Good day, everyone. Today, we are going to dive into a fundamental concept in time series analysis, the lag operator, and its role in dividing two components, MAQ and ARP models. Together, these are the building blocks of the more complex time series models, such as ARMA models. The goal today is to understand how these models are constructed and how they can help us analyze time-dependent data more efficiently. Let's begin by first understanding a lag operator. The lag operator, often denoted by L, is used in time series analysis to shift a variable back by one period. Essentially, applying L to a time series variable, say xt, means we are looking at the value of x at the previous time period, xt minus 1. To define this more formally, Lxt equal to xt minus 1. It helps simplify how we interpret and represent selected processes. For example, higher powers of L shift the variable further back in time. L squared xt means we are looking at xt minus 2. This operator is very useful when working with the time-lagged processes in time series state models, especially because it allows us to use shorthands for representing complex relationships. The lag operator have two key components. First, linearity. The lag operator is linear, L open bracket axt plus byt close bracket equal to alxt plus blyt. This means that when we apply the operator to linear combinations of two time series, it distributes over the terms. Compositions. Successive applications of the lag operator can be combined. L squared xt equal to L open bracket Lxt close bracket equal to xt minus 2. This property shows how multiple applications of the lag operator are combined algebraically. Now let's move on to moving average model, which helps us model the effect of past shocks or errors on the present value of the time series. The general form of an MAQ model is xt equal to mu plus epsilon t plus theta 1 epsilon t minus 1 plus theta 2 epsilon t minus 2 plus go on up to the term theta q times epsilon t minus q, where epsilon t is the error term or shock, and the coefficients theta 1, theta 2 up to theta q represent the impacts of these shocks from the previous time periods on the current values of the series. Using the lag operator, we can rewrite this model more concisely. We can express it as xt equal to mu plus open bracket 1 plus theta 1 L plus theta 2 L squared plus go on up to the term theta q times L to the power q close bracket times epsilon t. To simplify our mathematical notations, we use capital letter theta L to represent 1 plus theta 1 L plus theta 2 L squared plus go on again up to the term theta q times L to the power q. This is a much more compact and elegant way to represent the model. To make this more concrete, let's look at an example of an MA2 model, where the time series depend on just two past shocks. The MA2 model can be written as xt equal to mu plus epsilon t plus theta 1 times epsilon t minus 1 plus theta 2 times epsilon t minus 2. Again, applying the lag operator, we write this as xt equal to mu plus open bracket 1 plus theta 1 L plus theta 2 times L squared close bracket epsilon t. Next, we have optoregressive AR model, where instead of depending on the past error, like in the M8 model, the time series depending on its own past values. The general form of an ARP model is xt equal to mu plus find 1 times xt minus 1 plus find 2 times xt minus 2 plus go up to the term find p times xt minus p plus an error term called epsilon t. Using the let operator, we can rewrite this as xt equal to mu plus find 1 L xt plus find 2 times L square xt plus up to the term find p times L to the power p times xt plus the epsilon t. We can factor out xt and represent the equation as 1 minus find 1L minus find 2 L square minus up to the term find p times L to the power p. And the whole thing times xt equal to mu plus epsilon t. Again, to simplify our notation, we use a capital find L to represent 1 minus theta 1L to the term up to minus theta q times L to the power q. This formation is essentially useful because it allows us to factorize the autoregressive components of the model. Now let's look at the example of an AL2 model where the time series depends on its values from the past two time periods. The AL2 model can be written as xt equal to mu plus find 1 times xt minus 1 plus find 2 times xt minus 2 plus epsilon t. Applying the let operator, we represent it as 1 minus find 1L minus find 2 times L square close bracket xt equal to mu plus epsilon t. Finally, we combine the ARM8 model to form the ARMA PQ model, which includes both autoregressive and moving average components. The general term is xt equal to find 1 times xt minus 1 plus go on up to the term find p times xt minus p plus epsilon t plus theta 1 times epsilon t minus 1 and add up to the term theta q times epsilon t minus q. Using let operator, we can express it as a capital letter L times xt equal to capital letter find L times epsilon t. This representation gives us a powerful and compact way to combine these two models together into one equation. To conclude, the let operator simplifies how we represent and manipulate time-ladder processes in time series analysis. We have explored how this operator helps divide the MAQ and ARP models, how they combine into the ARMA PQ model. Thank you for attending my class today.